This part of the discussion talks about the analysis of scientific data, especially that in your researches or the nature of your researches is experimental, quantitative and experimental. So your researches really deal with numbers, numbers that are obtained in that moment that you are trying to measure or quantify categories so that you can proceed with comparisons. It's just that we need to be open to the possibility that by the time we make our measurements, errors can be identified or errors might just actually take place. No matter how careful we may be, errors can still be there. That is why in doing experimentations, there is a particular degree of error or percent of error that is given as an allowance. When scientific experimentations are being done, errors are given allowances, especially that the conduct of these experimentations involves human beings. Humans have the tendency, even if humans are very careful when they experiment, there might still be a chance that they'll commit some errors. Because of this, again, an allowance or a degree of error is given to these experimentations. What allowances or what degrees are given out? Usually, the tolerable percent error is at 10 or 10% is the maximum. But in the recent trend of researches today, experimental researches today, they find that 10% is just too wide as an error allowance. They find that if you give 10%, it's just giving so much consideration for error. Yes, an allowance is provided for errors, but we will not tolerate so much error. So now, it kind of gets toned down to 5%. 5% is the suggested allowance for the degree of error or percent error. There are even others who would even reduce it to 3%. The lesser percent error you have, the more reliable your data comes out to be. The wider your error is, or the larger the percent error is, the more questionable the data turns out to be. Are we going to follow, well, on this note, which one are we going to follow? In your case, let's give it until 5%. Let's give it until 5%. There is one kind of error though that is really, really strict. And the degree of error that's really strict. And it's that 1% degree of error. There are experimentations that limit it to a degree which is at 1%. Because these are the experimentations that are a matter of life and death. Failure in these experimentations might lead to the death of experimental units. For sure, you've seen commercials on televisions involving soaps, antibacterial agents, toothpaste. Familiar of the 99.9%? You should have seen that on televisions. The 99.99%. That's the allowance. That's where the allowance comes in. Why will they not put it at 100%? Diba, we might have asked ourselves that if they're creating such a good soap that kills bacteria, why can they not put it at 100%? Why will they not declare it at 100%? Because they're giving allowance for that degree of error. And up to what level? You have not seen anything that said this soap works at 95% or 95% of the bacteria have been killed. 90% of the bacteria, they do not do that because the products they're creating are for human use. Meaning, if the error goes beyond 1%, their product turns out to be very, very questionable. In your case, you're doing experimentations not involving human beings. So your error allowance will be at 5%. What errors, by the way, are we talking about? There are two types of errors that can be committed when dealing with scientific data. The first kind of error is an experimental error. The second one is a systematic error. Let me go to the second one first. The second error, the last paragraph on the discussion part of your module, the systematic error, is an error that is committed in relation to the use of particular measurements or devices, apparatuses. When these apparatuses are used incorrectly or that there was something neglected in the use of the apparatus, the error is committed. For instance, a graduated cylinder. I hope everybody knows how a graduated cylinder is going to be read. How you read measurements in a graduated cylinder. You assuming that you have been told to use a graduated cylinder and then you poured liquid inside that graduated cylinder. How are you going to read the measurement in a graduated cylinder? Joyce. Oh, have you had a chance to manipulate a graduated cylinder? Have you not? What about the STEM students? Have you had the chance to do experimentations with a graduated cylinder? Recall. How do you read the measurement on a graduated cylinder?
There is measurement markings on the side, sir.
There are measurement markings. Allow me to share a screen, ha. I hope I can draw a graduated cylinder well. Pardon me if I cannot. The graduated cylinder has this at the top. Then it goes down. Oh my God, there's a curve with this graduated cylinder. It goes down. Oh my God, that's another curve with the graduated cylinder. This graduated cylinder. And sometimes the base of the graduated cylinder is this. That's a graduated cylinder. Joyce, don't comment, Joyce. I know my drawing is so poor, Joyce. If you make a comment, Joyce, I'm going to eat you. And then, as Miguel has said it, there are measurement marks in a graduated cylinder. Something like this. And when you pour a liquid in a graduated cylinder, let's assume that the liquid is poured already and the color of the liquid is, how do we change the color? Here. The liquid has filled up this area. Here. You will not actually just read it based on wherever the how do you call the top portion of the liquid ends, because when you pour down a liquid in a graduated cylinder, the liquid is kind of slanted down and you'll read it based on the lower meniscus. If you read it based on wherever you find the liquid has stopped, that is not a good reading, because as said, you will follow the reading based on the lower meniscus. The liquid in a graduated cylinder will look like this. If you read it from this side, that's an error, because it's supposed to be read on this side. This is the lower meniscus that we are talking about. Or for instance, I'll stop the sharing of the screen now. For instance, you've been told to use a beaker. Everybody should know. No, not a beaker. A dropper. Remember the dropper that you use when you have liquid medication? That dropper? You can actually use that in experimentations. What if you were told to measure a liquid? You were told to put a portion of one liquid into another container using a dropper or perhaps into a petri dish. When you use the dropper, you did not notice that there was still some moisture inside that dropper. It's supposed to be dried up first, but you used it right away, even if there's already moisture inside that dropper. As it turned out, the water inside that dropper got mixed with the liquid that you placed inside the petri dish and then yielding a different result. That's a systematic error. Or you use perhaps a beaker that has not been cleaned yet, cleaned so well that there are residues of the previous liquid on that beaker. And when you mix liquids in that beaker, the residues got mixed up. So that will lead to a systematic error. To avoid this, you just have to be very careful. To avoid systematic errors, you just have to be very, very extra careful. The other error, or the first one, is the error on experimentation, the experimental error, which could either be precision or accuracy. Sometimes people interchangeably use these terms, but there's such a big difference between precision and accuracy. How does precision work? I'll do a share screen again. Wait, how do we clear? How do we clear this? Wait. Whiteboard. Hmm. How do we clear all drawings there? Let's assume the eraser. Let's assume that this is the target value. This is the target value. The one that you're seeing in red is the target value. Upon experimentation, you found that your values are here. This is where you found your values. This is what we refer to as accuracy. Because accuracy has something to do with how close your measured values are to the true value. The true value that we're referring to is the expected or standard value. Expected, accepted, standard, true value, they are referring to this one, the one at the center. The ones that are placed here, these ones, are the measured values. You may have a measured value, an obtained value. Please don't be confused of these terms. Measured, obtained, they're just the same. Standard, true value, expected value, accepted value, there the four of them are just also the same. Again this setup is what you refer to as accuracy. However, assuming again that this the red one, the bigger red circle, red dot is the true value, what if upon measurement your values are here? You have 6 values that are located here. They are far from the true value, but they are still close with each other. That is precision. Precision is something to do with the close togetherness of the values that you have measured. The closeness of the values that you have measured, even if they are not altogether close to the true value. That is precision. And again, the both of them are still considered errors. They are still accounted as errors. Why? Because technically, they are not the true values. The values you obtained are not the true values. Questions so far regarding precision and accuracy? In relation to that, there is a formula that will determine how good you are in that particular error. Meaning, is that error tolerable, or should that error require the experimenter to redo the experimentation? Because that's what's going to happen. If the error is beyond the limit, if the error that you have obtained is beyond the allowance, that's the decision is you should redo the experiment. Before we go into this formula, the one that's found in your module, I have to also tell you first that your experiments will not use this. Why? Recall, look at examine your researches. Do you have standard values? Do you have what do you call that? True values or acceptable values, accepted values? You don't. What you'll have are all measured values. Right, Joyce? I'll use your study as an example. Di ba in your first setup, you'll have measurements of plants, measured measured values. In your second setup, you'll have measured values as well. Third setup, you'll have another set of measured values. None, not one of those setups has a standard value. Good morning, Benjamin. Not one of those setups has a true value. Even with the study of Ivan and Benjamin, they don't, Ivan and Miguel, they don't have any standard value at all. What you have instead is a set of measured values. Question now is, what's the error between one measurement and another measurement? How close are these errors supposedly to determine, how close are these measurements supposedly to determine that the error is tolerable or not? Here comes the percentage difference formula, which is not found there. Percentage difference, how do you compute it? I'll try to put it on the share screen, ha. Share screen. Share screen. Here. Whiteboard. So here's the share screen for it. For the percent difference, this is percent difference, people. Percent difference. Percent difference is equal to the first measurement to be deducted by the second measurement all over. So all over, this is a struggle for me, oh my gosh. All over. Oh, there. This is really a struggle. I cannot help it. The average of the two measurements over 2. There. And this has to be, the numerator will have to be in absolute value. Because there's no such thing as a negative percent difference or percent error times 100%. There. Rai, remember, Rai, one night I called you about this. I called you that I called Raisa one time and told her that I talked with my physics colleague in the previous school about your researches, about your research project outputs. She told me na, like in the study of Raisa, no, I made mention of the study of Raisa, man, which is more or less true to all of your experimentations. Since Raisa's trial has 3 setups, so she'll take the average to constitute measurement 1. Like for instance, no, Rai, what is your setup 1, Rai? How many plants do you have, Rai, in setup 1? 3. Oh, setup 1A, setup 1B, setup 1C. Let's term that four. Let's term them that way, Rai, ha? Setup 1A, setup 1B, setup 1C, and setup 1D. The 4 of them will be placed at an average to constitute measurement 1. And the same shall be true to measurement 2. So Raisa will compare setup 1 to setup 2 by getting the averages of those measurements. Once Raisa obtains M1 and M2, she can proceed with this. For instance, setup 1A is equal to 12 cm. B is equal to 9 cm. C is equal to 11 cm. D is equal to 7 cm. What's the average? Do you have your calculators with you? Wait. The average here is 9.75. That's the average. This will constitute M1. What if upon computation in comparison to plant B, setup B, in comparison to setup B, Raisa found out that M2 is 11.7. This 11.7 assumingly has gone through this, it has already gone through this part. So what will Raisa do now? 9.75 minus 11.7, that yields a negative 1.95. Negative. But since you are to take the absolute value of the differences, that will now be turned into a positive value. So that is for the numerator. This is so elementary, no? 9.75 plus 11.7. The average of that is, wait, again, 9.75 plus 11.7 divided by 2. 10.75. 725 or 10.73. Let's just use 725. Then Raisa will proceed now to this formula to complete the formula. That is 1.95 divided by 10.75, 725. That yields her an error of 18%. There's a percent difference of 18%. Assuming, Rai, that this is your error, Rai, what shall you do? What should this error tell you? What will this?
Not accepted.
Correct. And that would require that you will redo the experimentation. So that's how percent difference works. But for now, for the purpose of this discussion, let us look at percent error. We will look at percent error. Anyway, for percent difference, that's something that you have to really consider when you do your experiments. No, when you obtain the data in your experiments. Do not wait for me to compute for percent error. There was one group in HNU. I sat as a panelist in HNU before. There was one group in Capstone that did not compute their percent error in identifying zones of inhibition. I did the computation while doing the paneling. Their percent error was really high. So that blew up their oral defense. So do not wait for the panelist or for whoever reads your work to do the computation of the percent error for you. You should try to do it yourself. But then again, for the purpose of this discussion, let's focus now on percent error, percent difference. I was talking about your percent differences. Now let's talk about percent error. How do we obtain the value of percent error? It's the expected value, standard, expected, true, or accepted value, minus the measured or obtained value, divided by the expected value. You should put that in absolute value and multiply it by 100%. It should be at absolute value because, again, the obtained value may be higher than the expected or standard value. If that's the case, when the subtrahend is higher than the minuend, that yields a negative value. To avoid a negative percentage, because there's none, you should put the computation in absolute value. That part of the formula in absolute value. Okay, let's try number 1. While doing a lab, a student found the density of a piece of pure aluminum to be 2.8 grams per cubic centimeters. The accepted value for the density of aluminum is 2.7 grams per cubic centimeters. What was the student's percent error? By the way, the ST is like this. The ST is like this, but it demanded that you should answer in a complete sentence. Therefore, if you simply place a number and not place it in a sentence, that won't earn any point. Your answer should be the percent error is. I'm still training you to develop the use of sentences ba. What's the answer for number 1? Benjamin.
3.7, sir.
Again.
3.7%.
3.7. But state the correct sentence, Benjamin, please. Give the complete sentence answer.
The student's percent and density of a piece of pure aluminum
No,
is
it can be very simple as
3.7%.
the student's percent error is, go.
The
Go,
student's
Benjamin.
percent error is 3.7%.
3.7%, correct. Please do number 2, Nicole. Nicole.
Wait, sir. Yes, sir. Wait, sir.
Go, Nicole. Nicole.
Wait pa, sir.
Go. Someone sent it to chat. This was from earlier. The problem in number 2 is a student took a calibrated 200-gram mass, weighed it on a laboratory balance, and found it read 196.5 grams. What was the student's percent error?
1.75,
Complete
sir.
sentence. Complete sentence.
Ah, the percent error is 1.75, sir.
Okay, 1.75. Wait, by the way, percent error. So what's the unit there? Percent. Okay, percent. Don't forget the percent sign, ha. In the ST, by the way, of course, there's a percent sign available in your devices. Please put in the percent sign. If it's not the percent sign, you can type in the word percent. Like PRCNT can really be placed there. But it has to really be there. Number 3, Raisa.
The percent error is 7.6.
Again, right?
The percent error is
7.6.
7.6.
What does this tell? What's the name of the? What? Since the pronoun here is you, the percent error is 7.6. What does this tell you, Troy? In number 3. What does this tell you? I mean, what should you do? Let's look at it that way. What should you do?
Proceed with the experiment.
Again, proceed with.
Experiment.
Will you?
No.
Redo.
It's about 5.
You will have. Will you proceed now right away to the proper experiment? Take
Restart.
note. Upon titration, the error yielded 7.6%.
Restart, sir.
Redo the titration process because it's not within the allowance of errors. By the way, let's try to make that as an agreement among ourselves. Let's limit our percent errors or percent differences at 5%. Let's limit them at that. Let's do number 4, Crisel.
Percent error was 3.88.
3.8.
8.
Let's try to double check. 7.6 minus 7.9 divided by 7.6.
1.6 sir.
Huh? Is it at 7.8? 3.8?
Check, sir.
It's important that you should identify 3 point.
3.94.
But what comes after 4 is a 7. It's
95.
3.995. Okay. Let's try to also agree. Let's limit it up to 2 decimal places. Diba? That's more or less like a general. When you do your sciences, no? The limits, the decimal places have always been, are more or less are usually cut at 2 decimal values. Take note, what's really important in this process is you identify first the measured value, and then you identify next the standard value. Like that in number 4. The measured density is the measured value. The known density is the standard value. Okay, let's go now to number 5. Nathan is ano? Nathan, please do number 5.
The student's percent error of a rope is 13.95%.
Again, Nathan, the answer is
Student's percent error is 13.95%.
13.95%. Correct. Number 6, please do number 6, Lexinet.
The percentage of error is 6.25%.
6.25%. Correct. What about Joyce? Are you fine to do number 7, Joyce? Please do number 7.
I don't have calculator, sir.
You can use your phone, Joyce. You can use your phone, man. Or what about Miguel, number 7, Miguel?
Bumuhay ng isang larawan ng masayang pamilya sa loob ng taon. Walang sinabing kulayan.
Miguel?
So for those who are following it, that means hindi kayo sumunod sa panito. Kaya gulit lang ang nangyayari sa FT3, walang kulay. No color. So if you need that color, ibig sabihin, kung walang
Miguel, etc. Troy, please do number 7, Troy.
I already saw those with color. I don't need to mention your name. I already saw it. If you will change that,
The same?
Can you do number 7, Miguel?
Yes.
Go.
Number 7. The percent error is 7.5%.
7.5%, correct. Troy, please do number 8.
Now, gusto ko basahin ninyo and I will
Troy?
read ang tula ang aking pamilya. So this is the time to unmute yourself. Unmute. Unmute. I will listen now. You will read. Unmute. I will know we're not reading, ha?
Troy?
Unmute. Unmute, children. Unmute.
Number 8.
Go ahead, ha? We will read together. Okay. Start ang aking pamilya.
The percent error is
Ang aking pamilya.
4.29.
Again.
Kilalanin ang
4.29.
aking pamilya.
4.29.
Sina
Number
at ina.
number 8.
Si ate at si kuya.
Are you sure it's at 4.29?
Ay kay saya pag kami sama
Benjamin, what's the supposed percent error on number 8?
lahat ng problema'y aming nakakaya. I like those origin. Very good. Itong si ama
Rai, what's the supposed percent error in number 8, Rai?
duda.
0.43.
Haligi ng
It's supposed to be 0.43%.